This is the fourth of a series of videos on probability, and this follows up on the last one. Now, on the last video, what we were talking about is we were talking about an experiment where you roll two dice and you add up the faces. And the key to that problem is that even though there's you can specify what the outcomes are in an ELO. And one way to get around that is to reformulate the problem. I'm going to show you today another way to solve problems where you have an experiment that's not ELO. And this is by defining what's called a probability distribution. And a lot of these problems you'll see solved without just kind of using common sense without a formal description of the problem. That's absolutely fine. But here's the idea of a probability distribution. So let's say that what happened is that you were wondering what the weather was going to be like tomorrow, right? So the experiment would be, in a sense, the weather tomorrow. And we're going to simplify the problem like we already talked about this. I'm not sure if that's how you spell tomorrow, so who knows. So anyway, we're going to do the experiment, the weather model. We're going to do it simplify. And let's say the outcomes are this. One is it could be sunny and no rain. And let's say you're like in some place like Hawaii where that's probably likely. So let's say that has a 60% chance of happening. And let's say another possibility is it's cloudy but no rain. And let's say that has 20% chance of happening. And another possibility is that it is cloudy and it rains. And let's say that has a 15% possibility. And let's say there's also a probability that it's sunny and it rains. And that has a 5% possibility, right? So in some sense, if you want to define this, a lot of times this will be given a variable name. This is like xi, and this is p of xi. You don't have to do it that way. But that's a fine way to do it. And in that case, this is clearly a non-ELO problem. Right? So what you can do is you can find the probability of simple events and compound events. The simple events are pretty easy. The probability that it is cloudy and not raining. Is simply 20%. 0.20. Now let's say the probability that it's going to be sunny. Now if you think about that probability it's going to be sunny, there's two ways it could be sunny. It could be sunny and not raining, or sunny and raining, right? So in this distribution, the probability of sunny and raining and sunny and not raining would be, the total number of ways it's rainy would be 65%. So add them up together. And the probability that it is cloudy, in that case, would be whether it's cloudy and no or cloudy and rain, and it's 35%. So that's a probability distribution. Sometimes they have something somewhat similar. They have something called a frequency table or a relative frequency table sometimes. And you do something very similar there. You might have a little bit more math to do, but let's say we look at a certain high school. Let's say it is Monte Vista High School. And let's say in Monte Vista High School there are 200 people that like ice cream. And there's 100 students that just absolutely hate ice cream. And there are, let's say, 300 people who like ice cream, but only on Tuesdays. Well, then you could do a simple event. The probability that someone hates ice cream is easy enough. the total events are 600. And the number that hate ice cream is 100. So it's easy enough. You just take all the people, which is 600, and of all the people, how many hate ice cream? 100. I know this is not a realistic problem because almost no one hates ice cream. Now let's say, find the probability that someone likes ice cream on any day. On some day. Well, if you think about it, there are people who like ice cream all the time, and there's people that like ice cream only on Sundays. Only on Tuesdays. But both of them like ice cream at some point. So that's going to be a total of 500 people that like ice cream on some day out of 600 total. And that's all a frequency table is. If we do what's called a frequency distribution or a relative frequency distribution, that's also called a probability distribution. Then all you're doing here is you're taking this table and you're dividing it by the total number. So let's do the MHS thing again. Here you have MHS, A, B, and C, but this would be 200 divided by 600. 100 divided by 600, 300 divided by 600. And the key is if you add all these up, the sum must be 1 or 100%. I know this problem seems contrived and very simple, but the thing I want to drill into your head is that they are simple problems, that no matter how complicated the problem seems to be, there's some basic common sense underlying it, and your goal is to try to use that. So let's do a relative frequency distribution or probability distribution in a more formal sense, right? The way they'd be is you'd have xi would be the outcome. And then you'd have P of xi. And let's say xi was 1, 2, 3, 4, and 5. The probability of xi would be the probability of each one of these things happening, and that has to sum to 1, or 100%. So this might be 0.4, that 0.3, 0.1, 0.7, 8, 9, 10. There you go. So we do. This is a very common thing. Now, there's no word problem to this associated, but this, a lot of times you get a word problem, you end up with something like this. There are 5 different outcomes here. They're not ELO, but each one has a given probability. So then we could do is you could do the probability, for example, that xi is less than 4. Well, let's say less than 4 would mean 1, 2, or 3. 1, 2, or 3 add up to 70, 80%. So you have 0.8. The probability that xi is even. Let's see what's even. Xi is even 2 and 4, so that's 0.3 and 0.1, so that's 0.4. That's how you read relative frequency distributions. And the key here is that all of these add up to 1. You could use some, if you know summation notation, the way we'd say that is we'd say the sum of Pxi is 1. But if you don't know summation notation, that's fine. It's just if you add all these up, you get 1. And that's called a probability distribution or relative frequency distribution.